to see so many faces here. We do not understand how pleased I am that Anna is actually standing here because in addition to being one of our amazing Clay Fellows, there was a little back and forth earlier about how to get her here, but in the end, she's here, and I'm super pleased that she's joining us at the CFA. So Anna got her PhD at Leiden. Before then, she was at Edinburgh for her MPhil. She, of course, is now a Clay Fellow. Before that, she received the MPIA prize. So she comes to us directly from Germany, and obviously you're Dutch. And I'm very, very excited to share the news that she got an ERC grant that starts in 2026. So that's a big one. Yay. And then she also, and this is really fresh off, this shall not be repeated beyond this room, she also got a major Max Planck prize. If you're familiar with the Lisa Meitner Excellence Program, she has been awarded one to start next year as well. So super glad that she's here, and I hope that you have a chance to talk with her. She does obviously amazing science, and yes, well, let's hear more about it.
All right, thank you. Thanks for the introduction, and this is my second day here, and it's actually great to be able to introduce myself to everyone so early on, and to show you a bit about my work, and then hopefully to spark some discussions and hopefully collaboration with many of you over the coming weeks and months. And so what I want to talk about today is really JWST, which has consumed my life for the past 3 years. So I joined the NIRSpec GTO team back in 2018, and of course when JWST started delivering data is when that took over my life. And what I really want to talk about today are the key surprises that have come out of JWST in the early universe, or at least the surprises in my biased view. This is by no means a complete list. But before I tell you about the surprises, I need to give you a bit of an overview of the status quo pre-JWST, because we did a lot of work, of course, in the past few decades as well. And so you're probably very familiar with this image showing a brief history of the universe. And as you know, we started out in the so-called dark ages, where the universe was very homogeneous, except for very small perturbations, which slowly grew and collapsed to form the first stars and galaxies. And if we fast forward 13 billion years, then we end up in the present-day universe with a very rich diversity of galaxies, and particularly at the massive end, where massive is sort of Milky Way mass and above. So we see diversity of structures, colors, and so on. And of course, the question is, how do we end up here? And from the ground, we've been studying this sort of the last few billion years in great detail. And with Hubble, we've been able to probe the first couple billion years. But it's only with JWST that we can actually probe the very first galaxies and the very first massive galaxies now. And this is important because if we perform sort of galactic archaeology and infer from local galaxies when they must have formed their stars, then we see the following picture. And that is that if you look at the most massive galaxies, actually most of their stellar mass was formed in the first couple billion years. And so if we want to understand how current galaxies came to be, then we need to go actually to these epochs to see how they actually formed. And so we know that a lot of mass formed in this era, but we don't actually know how, so how this actually proceeded. And so we do have a lot of models, of course. And so I'll start by showing you a movie. This is from the Fire simulation, showing a zoom in of what will be a Milky Way-like galaxy at redshift 0. And so what you see here is that material starts to fall into a dark matter halo, starts to form stars in the center of this. And you see this is a very dynamic process, so there's gas falling in, also being expelled continuously by various feedback processes. And it's only right around now, so this is redshift 2, 3 billion years after the Big Bang, that you see this structure emerging in the center. And it takes several more billions of years before you start to see something that actually resembles a galaxy like we know it in the present-day universe. So this is sort of 6 billion years after the Big Bang, and it's only now that we start to see these beautiful spiral arms appearing. I'm just going to let this play a little bit longer, not all the way to redshift 0, because in this particular box, not a whole lot happens, actually. But you see we end up with a beautiful galaxy. And so this is the picture we have in mind, a sort of turbulent early phase followed by gradual formation. And this is also what we see in observations. So for instance, with Hubble, we've been able to trace the disk fraction. So we can trace sort of, or measure how mature a galaxy is by its morphology or by its structural properties. And so we can quantify how many galaxies among the galaxy population are already disky as a function of time. And so near the Big Bang, there's nothing that looks disky, right? And a few billion years after the Big Bang, we still see a lot of galaxies that are very clumpy, and so in this turbulent early phase of star formation. And it's only sort of 5 billion years after Big Bang that we start to see these very nice organized structures appearing, so these rotating disks. And this is just a handful of galaxies, but of course surveys like CMOS 3D have mapped this out for hundreds of galaxies and showing that ubiquitously, sort of at redshift 2, we see these nice rotating structures, which indicates really how galaxies assembled their mass, right? So stars are formed in regulated fashion in these rotating disks. And these disks are not just rotating, they're actually also, we can measure more properties, right? So we know that they're also very baryon rich. And so that means that the centers of these galaxies are very thick disks consisting of just stellar mass and gas, and basically no dark matter. This is at redshift 2, and it's very different from what we see in the local universe, where, for instance, our Milky Way has actually quite a bit of dark matter on relatively small spatial scales. Now, this is all a couple billion years after Big Bang, so the question is what happens earlier than that? And we did know that pre-JWST that there was something funny going on in the early universe, and that's because we saw galaxies that look like this. So very red, compact sources that don't look disky at all. And if we infer their star formation histories, it looks something like this. So there's this very rapid burst of star formation that must have formed this galaxy, about 10 to 11 solar masses, followed by a period of quiescence. This is very surprising. First of all, this burst of star formation is surprising. And secondly, the fact that you have this quiescent phase in an era where, you know, star formation activity in the universe in general is actually only ramping up. And if we look more broadly at the galaxy population, we also see that something must be kind of happen or different about the early universe if we look at the kinematics. So if we look at this diskiness of galaxies as a function of mass and a function of time, then we see that this disk fraction drops dramatically towards lower masses and earlier times. And we also see this if we look at the velocity dispersion of the ionized gas itself. You see this sort of increases gradually towards the earlier universe. And so if we have to summarize, you know, a few decades worth of research and ask what do we expect or what did we expect prior to the launch of James Webb, then it is that if we go into this very early phase, we expect to see very turbulent galaxies, and some of which are vigorously forming stars, but overall this turbulence really must dominate. Okay, and then came JWST. I'll just show this picture. We have all seen the one on the left, I'm sure. But on the right, it's actually what is inside James Webb, and it's actually doing the hard work, right? It's not just the nice mirrors, but there are 4 instruments on board JWST. They all serve their own purpose. But I would say for extragalactic studies, there are 2 that have been really vital to a lot of the discoveries that you've seen in the news and on arXiv. And so first of all, the NIRCam is really sort of the workhorse of JWST. And in its first year alone, actually delivered a wealth of extremely deep imaging data, which was kindly reduced by Gabe Bremer. And so this is about 700 square arc minutes, which for a high redshift astronomer is a lot of imaging. It's wide area imaging. But it comes with incredible depth and resolution, right? So we reach 30th magnitude in a lot of these images, which is really incredible. And then secondly, with JWST, we have all these spectrographs on board. There are several here. And I won't claim that any are better than any others, but I will say that NIRSpec is the most fun instrument by far. And that is partially because I'm paid to say that, but also because it's true. So it's a very versatile instrument. So it's all these science modes. So regardless of whether you care about exoplanets or galaxies, we can agree that this is a great instrument. So it's all sorts of resolutions as well. And even with compared to other instruments on board JWST, it's like an order of magnitude more sensitive. So it's just incredibly sensitive at an incredible spectral resolution. And the mode that I'm most excited about, and why I say it's the most fun, is this multi-object spectroscopic mode, which allows for really efficient observations, really, that we can observe 200 galaxies in one go with incredible sensitivity. And so just to spend a few words on this multi-object mode is because it's so remarkable that it actually works. So there's this micro-shutter array, we call it, which is essentially this metal grid of little doors that you can open and close. And by opening and closing these doors, you can construct flexible masks, you know, on the fly, and observe 200 galaxies at one time. And the fact that this is crazy is because normally when you shoot something into space, you minimize the number of moving parts, but NIRSpec is happily floating at L2 with 250,000 moving parts, and it works. And so most people's favorite commissioning image is something like this, right, where you see really the remarkable clarity that Webb is providing. But actually, my favorite commissioning image is still this one, where you see the zodiacal light dispersed 200 times on a detector. And this came out right after I had accepted my job at MPIA. And I was like, okay, I could actually have data to work with during my postdoc. And so since this commissioning image, we've been taking data basically nonstop. And so there are by now multiple, more than thousands of hours of spectroscopy, several larger programs as well as many, many smaller programs. Here's a compilation of some of the larger programs where large is either in number of targets or sheer number of hours. And so this spans a pretty broad range. Even for surveys that might look similar in this diagram, they can target very different types of objects. And so having all these programs is actually extremely important. And in the rest of this talk, I'll show results actually from the two opposite ends of this diagram here. And so we've amassed all sorts of data, imaging, and spectroscopy. And the question is, what do we find? And so really, when we look in the early universe with Webb, we come to one conclusion, regardless of what you look at, right? If you care about galaxy structures, stellar populations, black hole properties, chemistry, we all find the same thing, and that is that galaxies are maturing extremely rapidly in the first 1 to 2 billion years. And so, like I said, this manifests itself in 3 or multiple ways. I'm going to talk about 3 of them today that I have personally contributed to, but there is actually much more still out there. And so to start with what I showed you before, with Hubble we saw all these very clumpy-looking galaxies, and so we thought that star formation must have been very turbulent in the early universe. But if we look at the exact same systems with Webb, then we actually see that these same galaxies are very smooth structures, and what we thought were clumps are actually just very nice spiral arms in these systems. And so what we see is that there's actually a surprisingly large number of smooth disky systems in the early universe. And we see this everywhere, regardless of with which method you look. So for instance, Galaxy Zoo has done a large run recently where they asked people to visually classify galaxies, and you see a lot of these smooth disks. There's various machine learning methods, that also pick out a lot of these very smooth systems. And then you can do all sorts of parametric morphological measurements as well. And what jumps out is that with JWST, we see that this disk fraction that you infer just by essentially quantifying whether you see something that's smooth and sort of elongated is much higher than what we had anticipated or what we had measured before from Hubble. And so this is surprising. Of course, the caveat here is that if you see something that looks disky in imaging, it doesn't actually mean that you have a disk, right? So you can imagine you have this sort of elongated ellipsoidal structure here, which can happen if you have accretion happening. That doesn't actually mean that it's rotating. And so the only way to figure out whether you actually have disks, so to figure out how stars are forming in the early galaxies, is using spectroscopy. And so this is where the GTO data really were vital, as they targeted many galaxies with both shallow and deep depths, and focusing on a pretty general census of the galaxy population, targeting largely, or not exclusively, galaxies we had seen with Hubble as well, so sort of blue star-forming galaxies with all sorts of resolution. So that's really great because you can then simultaneously constrain stellar populations as well as the dynamical properties. And so in this very first deep data, actually, I started looking around. So this was really a few months into the mission, and found galaxies that look like this. So here we're looking at redshift 7, and you're looking at O3 emission lines. And so that's by itself is already remarkable. What you see here on the left are NIRCam images, and you see that they're spatially resolved galaxies. And on the right, you can see the spectra, high-resolution spectra. And if you have a trained eye, then you can see that there's a little velocity gradient in these galaxies, which is really remarkable. Because we're, for the first time, measuring kinematics from ionized gas in the first billion years. And we're not just doing that, but we're actually also probing an entirely new regime in doing this, right? So with CMOS, we were able to probe these massive galaxies primarily and more extended galaxies. But with Webb, we can now actually resolve the very small, compact galaxies in the first billion years that are the progenitors of these galaxies we have seen with CMOS. And so actually going from this to parameters on how velocities and so on is kind of challenging. So I'll very briefly show how we do this, because this is what I spent probably most of my time on in the past couple of years, is to develop forward modeling tools to actually extract physical parameters from web data that is actually very much non-trivial. And so what we can do is we can parameterize a galaxy by its velocity field and a flux profile. And then what I've developed is essentially this forward modeling approach for the instrument, right? Where you can translate these parameters into actual, this handful of pixels that you see here, coupled also with the calibration program that's still ongoing. And once you have this in place, you can actually start to compare it to the real data that you have, right? And once you have this, you can imagine you can do sort of MCMC to figure out what the velocity profiles actually are of these early galaxies. And the outcome was surprising. So if we look here, for instance, at the velocity dispersion of the ionized gas itself, then based on what we found at lower redshifts, if you extrapolate this, you would expect the velocity dispersion to keep increasing towards earlier times. And that's not really what we're seeing. We actually see that the velocity dispersion is relatively low, or constant with respect to cosmic noon. And the same is true if we look at this V over sigma. So that's essentially a measure of the rotational support, right? So you can very roughly say that everything above this dotted line is sort of consistent with being a rotating disk, and everything below this dotted line with being a very dispersion-supported system. And so based on what we knew from cosmic noon, we would expect, that there's this trend downwards towards higher redshift. And so we would not expect to find any point-like sources to lie above this dotted line. And so the fact that we do find systems there is surprising, because it suggests that we might actually be seeing rotating disks in the first billion years in these very low mass galaxies. And so it tells us something very fundamental about how galaxies are forming their stars in this epoch. The other major surprise to come out of this is that the dynamics give you also a mass, right? And so if you compare this then to the stellar mass, what we actually see is that the stars make up only a tiny fraction of the total mass that's in these systems. And that's very different from what we see at lower redshifts, where generally the stars are the dominant component, if not fully accounting for the total mass. And so even if you account for some gas mass here, actually, this doesn't fully explain the mass budget that we have. And so what it suggests is actually that we have dark matter in these galaxies, but on spatial scales of 1 kiloparsec, which is actually very surprising. And so this is, of course, just a handful of galaxies. And so with a student at MPIA, Jakob Mürle, we've been extending this work to several thousands of galaxies. And what you see here, so this plot, it's still in prep. But what you see, the y-axis here is roughly dynamical mass, and the x-axis here is the stellar mass. And you see what is interesting is that at the high mass end, the stellar mass and dynamical mass are roughly equal, right? They follow this linear relation. And then there's this flattening happening at the low mass end, which tells us that there is something very fundamentally different about the mass budgets in these low mass systems. And this is true at all redshifts, actually, which is quite interesting. And so it suggests a very high dark matter content, possibly gas content in these galaxies. And so what do we make of this? Well, so we turn to the simulations. And simulations do kind of predict this. So if you look at TNG 50, for instance, and just do very simple apples to oranges comparison, you see that the simulations predict that the baryon fractions, and even in small spatial scales, are actually very low, consistent qualitatively with what we see with Webb. And so this might be tied to the fact that we see these rotating disks as well, because if you have essentially this very deep gravitational potentials, right, so here set by dark matter, then you might also be able to stabilize essentially your disk at the same time. And so these Webb observations are really showing us really how galaxies are forming and growing in this very, very early phase. All right, but everything I've shown you so far is based on looking at galaxies we knew from Hubble, but looking at them in much greater detail and much better resolution. But what was really surprising with Webb is actually the second puzzle. And that is that we found a whole lot of galaxies that we had never seen before, right? That were too red for Hubble, and often also beyond the resolution limit of Spitzer, so it was blended with other nearby stuff. And so there's a whole zoo of red objects out there we have never seen before. And this really, I think, was the biggest or the most important topic that our field has worked on in the past 2 years. And so these objects they have the same red colors, but they come in all sorts of shapes, sizes, and also luminosities. And what is interesting is when you start looking at their SED properties. So here is probably the most contentious paper from the first year of Web, maybe even still today. It's a paper from Ivo Labbé where he stacked essentially the SEDs. And what you see in green here is what we found before of high redshift galaxies with Hubble and Spitzer. So essentially SEDs that are consistent with being star-forming galaxies with strong emission lines. And these red sources from JWST turn out to have this very strongly increasing luminosity at longer wavelengths, which you can interpret as light from old stellar populations or very strongly dust-reddened stellar populations. And typically that means that you have very massive stellar populations. And in fact, the light that hides underneath this red curve is so massive that it actually exceeded our expectations from the stellar mass function by an order of magnitude or even 2 orders of magnitude. And this was very controversial, of course, because actually to form galaxies that are this massive in the first billion years requires possibly changing our cosmological model. Or even if you don't believe that you have to change the cosmological model, it requires every single baryon in a halo to be converted into a star. And that is, of course, a very difficult thing to do. And this result was based on just a handful of sources, but was quickly extended to hundreds of sources in other fields as well, and really sparked a major controversy. Of course, this is all based on imaging, and so naturally and rightfully so, there's a lot of skepticism. Where if you have broadband photometry, then you need to somehow estimate redshifts and stellar masses, and both of these are very difficult to do. And so if you have an SED that looks like this red curve here, you can explain that. So Ryan Ensley nicely showed this in his paper with very, very different models, right? So by star-forming galaxies with strong emission lines, or in the middle here is this old galaxy with a very strong Balmer break. And on the right, you can even concoct some really weird AGN models that are just pure emission lines and almost no stars. And so the uncertainty in the stellar mass here is really several orders of magnitude, and so it's in some sense easy to explain away these very difficult results otherwise. Clearly, to really answer this, we need spectroscopy. And so this is really was the primary goal of my own program called RUBIES, where the R and the U stand for red unknowns, and the rest of the letters I'll leave you to figure out. The S stands for survey. So this is a team of about 35 people spread across the globe. Gabe Bremer is the co-PI of the program. I'm just showing some faces here of results, whose results I'll be showing in the next couple of slides. And so what RUBIES did was to survey a pretty wide area, or at least for JWST terms. So we surveyed 2 extragalactic deep fields covering about 5,000 galaxies across all sorts of redshifts. And we prioritized anything red without any photometric redshift information or without any morphological information even. We just said, just put anything red on a mask, and then we filled the mask with normal galaxies, but with a very well-quantified selection function. And that is very important because if you observe a very rare object, you want to say, how does this fit into the general galaxy population? Like, how can I estimate its number density, right? And so we spent a long time essentially developing this. And here you just see a compilation of some of the spectra. You often see these spectra compilations sorted by redshift, but because our survey probes a huge range in color, you can actually sort them by color as well, which is kind of nice. So you see at the blue end, you see very strong UV light with strong emission lines. And then as you go to redder colors, you see the Balmer break emerging, and these emission lines slowly starting to fade away, which is kind of cute. And so, as I said, between surveys, there are actually huge discrepancies. And so, comparing to some of the other large programs, you see that we all kind of probed the sort of bulk of the galaxy population, but really only our survey is targeting several hundred of these very red sources. So what do we find with all these spectra? Well, the thing we wanted to look at was, of course, the stellar population properties. And so that is something we can do. And first of all, I'll show you what a normal star-forming galaxy looks like, where you're probably familiar. We have strong UV emission, strong emission lines, a classical young star-forming galaxy about 1 billion years after Big Bang. And so the surprise really came when we started looking at these very red sources. And instead of strong UV emission, we found something like this, where you see this very strong Balmer break, as well as instead of emission lines, we see actually absorption lines. And these are telltale signs of having a very old, massive stellar population, but only 1 billion years after the Big Bang, right? This galaxy is more massive than our own Milky Way. And so actually just the existence of this source is already a problem for a lot of galaxy formation models. And it gets worse when you start to model the stellar population history or star formation history of this spectrum. And so if we do this and we believe, so we apply our stellar population modeling like we do for all sorts of galaxies in the nearby universe, then you get this pink curve out. And what this says is that there must have been this huge burst of star formation at a redshift of 10, right? So a few hundred mega years after the Big Bang. And I just told you that we designed our survey in a way such that we can estimate number densities for our galaxies. And so that means that we can sort of estimate order of magnitude what sort of halo this galaxy must have lived in. And what this means is that if we do this, we also know how many baryons were roughly available at a given time epoch. And so if we believe this pink curve, then essentially this galaxy must have converted more baryons than there were available into stars. And of course, this is not possible. But it does say that we need very, very efficient star formation to form a galaxy like this. And you see also this blue curve here. I'll come back to this a little bit later. It's essentially if you assume different chemical evolution for your galaxies. But regardless of which curve you believe here, even if you believe the youngest possible solution, we require very, very efficient star formation in the first billion years to form these very massive galaxies. And this is just one source. We quickly actually broke our own record and found another. So this is Andrea Weibel, who actually defended his PhD last week. And he found a galaxy even younger, so just 700 million years after Big Bang, but kind of showing a similar spectrum, a bit more noisy, with, again, these tentative absorption lines and a strong Balmer break. With the same story, just having this very, very massive old system in a very young universe. What is kind of nice about this galaxy as well is that it's extremely compact, so it's about 100 parsecs in size. And so it's about as dense as the densest quiescent galaxies at lower redshifts. And so what this means is that this galaxy is actually on track to being the core of like an elliptical galaxy in our nearby universe. But it was already put in place just a few 100 million years after the Big Bang. And so by now, with another PhD student, Zhongcheng Zhang, we've compiled the whole survey and found several dozen of these massive galaxies. And then we can actually start to compare to different theoretical models, right? And what you see is that there's this pretty major tension at redshifts beyond 3 between basically all current state-of-the-art galaxy formation models and our observations. And this is just from our own survey. If you don't believe this, then actually MJ Park, who was here, compiled essentially every single JWST paper available, at least at the time. And the thing to take away from this plot is just that there are many, many galaxies out there like this. And what is remarkable that is, these observations all probe independent sightlines, really, with JWST. So what this means is that everywhere we point with James Webb, we find one of these record-breaking galaxies. And so with the first one, you can say, okay, we're just lucky. Cosmic variance is important when we have these pencil beam surveys. But at some point, if you point the telescope in a random direction and you find a source like this every time, cosmic variance is no longer a way out to explain away these results. And we actually need to confront, really, our theoretical models as well. And then finally, well, this kind of grew out of the previous, is a major puzzle that I think has taken over many research groups, including our team. And that is the puzzle of these little red dots. And so we came from this at the angle of trying to find massive galaxies, disproving them or not. And in the end, we were all tricked into studying black holes, including myself. And so this kind of goes back to what I was showing before, where we have this SED that has a very peculiar shape. So we call this a V shape. So there is this sort of blue UV. It's blue in F lambda, but flat in F nu. And then this very strongly rising red continuum. And so as I showed, we can explain this in different ways, right? Where you can imagine there's some combination of emission lines. But what was really the most debated was this model in the middle, where you have the old galaxy solution with a very strong Balmer break that essentially explains your SED. And so in the paper of Ivo Labbe, that was the middle model was kind of what was assumed or what came out of the fit. And it was also the one that was least believed by the community. And so in Rubies, we took spectra of all of the sources in this original paper, as well as many other little red dots. And I would say the biggest surprise was when we started looking at these spectra, is that this Balmer break feature is actually there. And so we wrote a paper, Bingji Wang wrote a paper saying, we see Balmer breaks in these little red dots. And so that means, or typically that means we have evolved, or we have A stars really in these galaxies, and within the first 600 million years, we call it an evolved star population. And so the key implication of that is that this major tension with cosmology has not actually gone away by taking a spectrum. Right? The redshift remains the same, and actually this, at least naive, at face value, this Balmer break suggests that actually there is an old star population there. Of course, there are also people that don't believe this, including ourselves. There are other features in the same spectra. So here you see the O3 and H-beta emission lines, and what you see here is there's this very broad component in H-beta, right? And normally that's a telltale sign, or at least when you have a narrow O3 line and a broad Balmer line, there's a telltale sign of an active galactic nuclei. And so the other option that was strongly proposed is that actually little red dots are just active galactic nuclei, and their red color comes from strong dust reddening in these systems, which is also problematic because in doing so, actually the bolometric luminosities of these sources become extremely high. And so what this means here is these data points are all just little red dots. And so little red dots alone essentially account for all the bolometric luminosity that is in a galaxy formation model already. And then we still have other AGN that we know are out there from JWST. And so there was something very strange also about this explanation. And you might wonder, why do we need either or, right? Why does it have to be either a massive galaxy or dusty AGN? Well, we also tried stuff in between. So just, making some combination of stars plus a dust-reddened AGN. And we showed that this kind of works, but you have to really fine-tune your solution so that, the AGN always comes in just at the Balmer limit. And that's slightly uncomfortable, but hey, for 2-3 sources, that is fine. We can fine-tune, maybe. The issue is then that you have a galaxy actually that's still extremely massive and extremely compact. And so it's actually so compact that you have a galaxy, so that's these red data points here, that's about as dense as the nuclear star cluster of the Milky Way, but then 1,000 times larger, which is, of course, very hard to imagine. We don't see remnants of that in the local universe. Finally, to really highlight the tension here is, for 2 galaxies, you can say, I'm going to fine-tune my solution. But so Raphael Widding actually searched the whole Rubies data set and found 40 galaxies like this, or 40 little red dots that show the same spectral features. And so we call this the beach ball plot. But really what it shows is that if you select a source with a V-shaped continuum, and you select for it to be a point source, then all of them turn out to have broad Balmer lines. And the other way around is also true. If you have a V-shaped continuum and you find a broad Balmer line, then it's automatically actually also going to be very compact. And so there's this population of sources out there, essentially, that share the same common characteristics that naturally drop out of the data. And we see these at all redshifts, at all sorts of magnitudes. And what this means is that these sources are not rare, right? And so to explain them, we actually need a dedicated model rather than having some fine-tuned solution for several dozens of these sources. And there are hundreds more just photometrically. And so I would say the field is kind of stuck. I mean, there are definitely a lot of theoretical explanations proposed, but from an observational standpoint, we were definitely kind of stuck with models that were very awkward with very strange implications. And then earlier this year, we found some sources that really helped kind of push for a breakthrough in our understanding, I think. And so here what you see is a spectrum of a massive quiescent galaxy that I showed you before. So you see this strong Balmer break. Here are some little red dots that we've been studying to death. If you work on little red dots, then these phone numbers probably are familiar to you. And what you see is, this is how these composite models work. You see, up to the Balmer limit, they kind of look like these massive galaxies, and then beyond that, they don't anymore. And then we found a source that looks like this. We called this the cliff. I don't think I have the image of what it's named after in my slides anymore. It's named after some Irish cliffs because it looks very similar. But what is really the key feature here is that this Balmer break is extremely strong, like much, much stronger than a normal massive galaxy. And we then found actually a second, so Rohan found a second 2 months later, coincidentally, actually 60 arc seconds from this source. And so they kind of, they lie well above, if you look at Balmer break as a function of redshift, they lie well above anything else we've ever seen. And actually, I think I would dare say that even in like large data sets like Sloan, there's just nothing out there that looks like this. And so we tried very hard to model these sources with all our standard tools like we had done before. So we run, all our stellar population modeling codes. But we had to conclude that nothing really works. And in the end, we actually resorted to fitting individual stellar spectra to see if there's anything like it that even fits the data. And so what you see here, these dotted lines are individual stellar spectra just straight up from the Milky's library. And then solid is with some very, very steep dust attenuation. And of course, normally A stars, so that's the blue and purple here, kind of make the strongest possible Balmer breaks that you can imagine. But even if you add very strong dust attenuation, you still cannot explain this spectral shape. And so what this means is that we don't have some post-starburst galaxy here. We really have something else. And there's this red curve here that's actually kind of interesting because it shows that certain stars do come somewhat close to reproducing this. And this is a key feature for a little bit for now. And so what are we dealing with? Well, we have this spectrum, and we were actually able to rule out every single model we had. And then you're left with nothing but just looking at the data at face value. And so what we see here, first of all, are these very bright emission lines that are also broad. So we have some fast-moving gas that's very luminous. And of course, that points normally to being accreting massive black holes. We see that there is this very red thermal emission, which points to there being optically thick gas. And finally, we have this very high-density hydrogen gas because we see this very, very strong Balmer break. And so if you take the data at face value, it says, I have some rapidly growing black hole that's embedded in something like a stellar atmosphere. And that's, of course, kind of crazy. So Rohan called this a black hole star. This is a PR image that's certainly not to scale nor accurate. But it is really a wacky conclusion, and since then, of course, we've been trying to figure out, I can make this slightly more scientific, and have a PowerPoint diagram, how to model these sources really from scratch, right? So developing sort of cloudy models for now, where we have some source and we pass it through a slab of gas, and you can see with actually just a few weeks of effort, we can produce spectra or model spectra that kind of look like what we're seeing, of course, with caveats in the UV and also in the near infrared still. Okay, so I've shown you there are all these surprises, and a lot of models seem, well, if you go to a Galaxy conference, you'll hear the phrase often saying our models are broken. But how do we move forward from here now that we've seen all these crazy objects? And I think we need to be very careful when we say what is actually broken. So there's models we use for parameter inference, and then there's actually galaxy formation theories, right? The most extreme being our lambda CDM model. And then the question is, to what extent do we actually need to modify our theories? Probably we don't need to modify cosmology for high redshift galaxies. And so we've been working on several different angles here. I'll just very quickly kind of show a few of these. So for instance, for the kinematics, to figure out whether or not we're dealing with disky systems, we've been actually trying to test how well our code actually works. And so this is work done by Anirudh at MPIA, where he's taken TNG50 and produced, these are the very first NIRSpec MSA mocks, like really realistic mocks, and then running the same kinematic inference for them to see how well this actually does. And you see that the residuals here look pretty great. But if we look at the parameters that come out, it's kind of scary. So the dispersion, there's sort of a one-to-one, also for the velocities, but with very, very large scatter, right? And so this means that before we conclude that anything is truly disky, there's still actually quite a bit of work to be done. The same is also true for the stellar population modeling. So I showed this before, where we have this large uncertainty in the star formation histories of these very massive galaxies, where some are really, really problematic for galaxy formation models, and others require maybe less tuning. The issue is that we're using stellar population models that were trained or tuned to the low redshift universe, right, where the chemical composition of galaxies is very different from the early universe. And so this was nicely demonstrated by Eliza Beveridge, showing that if we look at the iron and magnesium over iron ratios in these early galaxies, it's very, very different from the early or from the late time universe to which these models were actually calibrated. And so there's great progress there now, of course, also again by MJ, who has developed actually stellar population templates that account for this alpha enhancement. And so the key step forward, we're actually working with MJ right now to reanalyze this galaxy on the left here to figure out what the star formation history actually looks like if you account for the full chemistry. I do think that by changing our models, we're not going to fully resolve all this tension, and so there is definitely a lot of scope on the theoretical side as well. Very early on, there was a lot of interest in this new proposal for feedback-free star formation that you might have heard of. And what this does essentially is that it allows for the production of a lot of stellar mass or light also on very rapid timescales. This is by no means the only way to change theoretical models, but it was just one proposed way forward, and I do think that something like this might be necessary. I would say the only place where we're really still stumbling in the dark is this, where we've now shown for 2 objects, or maybe 3, that we really need a model like this, right? Something very strange that looks like a quasi-star. But whether this is an AGN or not, or whether it's a supermassive star, is still a huge debate. And it's also actually a major debate whether or not all little red dots are like this. And so this is work that is still, I'm going to skip through this, yeah. So we've shown that at least a few of these sources are not dusty, but actually reddened by gas. But we've now been extending this, or trying to extend this to the much larger population of little red dots. And so actually in the paper that I'll put on arXiv very soon, we've compiled about 110 of these little red dots. And we find that ubiquitously, they're very well described by black bodies. Black bodies of actually very similar temperatures. And so what you can do when you have this is start look at correlations. And first of all, you can start look at something like an HR diagram that we're very familiar with, in our own neighborhood. You can tell that I'm not a stellar physicist because the axis for the temperature is flipped. And so it should actually look like this, and I'm going to fix this before putting it in arXiv. But what you see here is something very interesting, and that is across 2 decks in luminosity, little red dots all have the same or almost the same temperature. And so what this means is that we're probably dealing actually with something like stars that are on this Hayashi track, right, that we know of very well. And the temperature is almost the same as the real Hayashi track. It's actually slightly higher for little red dots. But what it's really saying is that we're dealing with essentially photospheres generally for the LRD population, which is, I think, really remarkable. And so how we then actually explain this is the next question. And I hope to discuss that with some of you actually in the audience that are working on this. There are many ideas floating around to explain this as quasi-stars or other types of AGN embedded in dense gas, or whether we don't actually need a black hole in the center. It might just be nuclear fusion in a supermassive star, and so on. All right. So with that, I'll leave you with my summary, and that is that JWST spectroscopy has been really amazing and really powerful in showing us how galaxies actually grow in the early universe. So it has revealed a lot of surprises, these mature early galaxies that are mature in various different ways. And these results actually might require quite substantial revision or even development of new models. And so finally, I'll just say that all the data that I've shown you in this talk are publicly available, thanks to Gabe Bremer. And so if you scan the QR code, it will actually take you to the website where this is hosted, and it has this nice image you can browse where you can open spectra yourself and also download it. So thank you.
Super exciting talk. Plenty of time for questions, and hopefully this is very thought-provoking. Yes, do we need a mic? Is that
yes, okay. Because there's an audience online. Thanks for the great talk. So in the quality star work that you showed, like various column depths of the hydrogen that you kind of made it fit to the data. So can you extract something more than the column depths, like the radial scale of this, like optically set envelope, so that you can get sort of the mass well understood?
Yeah, very good. Yeah, so this is exactly what we're working on now, actually also with Rohan Naidu at MIT, is to see if you accept the stellar analogy, then it opens up a whole toolbox, right, from people that have been studying stars for a very long time. And so what this means is that if you accept that these are stars that are like on a Hayashi track or whatever, you know the bolometric luminosity, then it automatically, from the Stefan-Boltzmann law, gives you an idea of the size, right? And so this is about 1,000 AU in size, which is large for a star, not very large for a black hole. And then the key question is still the mass. That is actually, we're trying to see if we can model that somehow. It's very hard, because it's very degenerate also with metallicity. So yeah, there are claims of, there is one claim of doing a dynamical mass measurement for one of these little red dots. It's very difficult because you're pushing JWST to a limit that I'm not sure that we can trust the calibrations. And then whether we can do it from SED analysis, I think it's still TBD. We're definitely trying to see if we can. Yeah.
Thank you.
Hi. Well, very exciting talk. Your black hole star. Is there any way, I mean, depends on the accretion state of a black hole, if a black hole is there, but I would think X-ray measurements may help?
Yeah, so the little red dots are notoriously X-ray weak, and so not detected in any stacks. And there are two ways. One of them is if you have very dense gas, like high column density gas, 10 to the 26, then that would block any X-rays by itself. The other suggestion has been that if you have super Eddington accretion, then that might also naturally not produce a lot of X-rays. And so then it becomes very hard to actually constrain masses or accretion rates. Yeah, I recently sent a message to a collaborator saying, should I say anything about accretion rates in my proposal for James Webb? And she said, well, do we even know the bolometric luminosity? Yeah, I don't have a good answer. Yeah, the X-ray is very, very difficult.
Okay, got two questions in the back here, so you guys can just pass the microphone.
Thank you. And I have a question on the black hole star model that has been puzzling me since like you put the paper on archive. That you have this optical thick thermal envelope at outside, and also the ionized source inside. That means the ionized photon, like H alpha traced by H alpha, never escape out. So there must be some viewing angle effect that in some of the angle you see the broad H alpha emission line, and the other angle you see. Or other angle, you see the optical thick envelope. I don't know whether you have considered this in the further research or not. And I think this makes it fundamentally different from stars, because stars, you can generalize them with 1D, but this you really need a 3D model.
So I'm not a huge fan of the viewing angle argument. And I think, right, so the issue is that if the source produces ionizing photons, and so the source produces, or the region around it produces Balmer lines, right? Then if it's optically thick, then you actually shouldn't be seeing the Balmer lines, that's the point. There are a few ways out of there. And so one of them is the fact that if you have this very dense gas, then electron scattering can broaden your lines. Both electron scattering and resonance scattering actually can broaden your lines kinematically. And so this means that, yes, your gas is optically thick at the wavelength of the Balmer transition, and we do see absorption at this wavelength. But in the wings of these lines, you're not optically thick, and so those can pass through. And so kinematic analysis for these objects actually shows that a lot of them are very consistent with exponential profiles or some combination. And then what can happen, why you get still narrow emission, is because in these outer regions that are not optically thick or less so to the Balmer lines, the gas is still very dense, and so it's actually very conducive to just collisional excitation of the Balmer lines. And this picture holds, so actually in this paper that we explore all sorts of correlations. And so there is a trend between like Balmer break strength and essentially some of the luminosities. Like, so there, it goes in the direction of actually there being collisional excitation there. I think to show it in individual sources is also possible. But there is a population trend consistent with that. Yeah.
Thanks for the great talk. I'm sorry, I also have a question about the cozy star. Just about the mass of the star itself. First, how do you make sure this star, this black hole, is really sitting at the center of this gas and stays there for long enough time to accrete? Also, like, what would be the mass constraints of this central black hole itself? Because, as you mentioned, to have no X-rays or low X-rays, you need super Eddington accretion, so this object must be stellar mass-ish black hole that you are then accreting tremendous amount of gas on, right?
Right. So I would say, so on the mass issue, the claims are, so the luminosities of these systems are very high, right? And so I think a stellar mass black hole would be very hard unless you really have crazy accretion rates. And so the mass range that, at least the bubble that I live in, is thinking of is more like 10 to the 5, 10 to the 6 in solar masses for a black hole. But for the whole system, it's actually probably higher. Right, so to form an envelope that's actually dynamically stable requires like at least something that's as massive as the black hole and probably actually more, like 10 times more massive than that. And then there are some groups that still believe that the Balmer lines actually trace a broadline region, and they come to actually higher masses even, like 10 to the 7. So there's a huge debate there, and I mean, I think the reason why you're thinking of 10 to the 5, 10 to the 6, it was partially luminosity, but also partially it fits. It would fit in our theoretical models. You know, like you can hide an ocean of 10 to the 5 stellar mass, 10 to the 5 solar mass black holes without really having any problems. But yeah, I wouldn't claim any sort of measurement has been properly made for this, and especially not for how the accretion then actually happens within the system like this, right? Like, rightfully so, you say whether it's even centered or not, I have no idea.
That's why I think maybe the supermassive stars, as crazy as they are, there you actually have a clear measurement of what the radius would be, and they could also do the same thing a quasi-star is doing, but they'd be much easier to disprove, let's put it that way.
Maybe, yeah, I mean, I'm totally actually agnostic to what the source is. Well, maybe I should say this, and then actually the title of my next paper has AGN in it, but that's mainly because, it's a very short way to say, you know, what a system is. But yeah, personally, I am not convinced that we have shown that there's a black hole there, right? And so even claims like we see barely any high ionization lines in these galaxies, so we barely even see helium-2, right? And there's a recent claim of seeing iron-7. I don't think that's correct. But even, yeah, and then there are some people saying, well, we see iron in emission, and so clearly that points there being a black hole, but there's no reason why a supermassive star could not produce irons, right? So yeah, I think the jury is still out. Actually, we're taking data today, like right now. James Webb is taking a deep spectrum of the very brightest little red dot in the uncover field, which has all sorts of emission lines. And we might see high ionization lines there. That's TBD in the coming week, I guess. But yeah, it would be great to chat more.
We have one last question.
I apologize. I'd like to ask a question about the quasi-stars, but not about the models. I think in one of your earlier slides where you showed the first and then the second object, if you could go back to that, I thought it showed that one of the objects was at a very low redshift, around 4.
3.5, yeah.
3.5, which kind of surprised me because I'm ignorant of these things. Why wouldn't that have been seen by an earlier satellite? Because it's at a much lower redshift. But it also made me wonder, what is the redshift distribution of all the little red dots you've seen?
Yeah, great questions. So yeah, a lot of these sources are detected in Hubble imaging. It's just that based on Hubble, you would have never ever concluded that these are, you know, the crazy things that they are. And so this source, it is very faint, I should say. So it's like 23rd magnitude at 4 micron, but in the UV it's 28th, right? So it is, these sources are detected by Hubble, but they're usually very faint, fuzzy things. Even some of them not shown here. Actually, it's it's this dot here. We have a ground-based spectrum from 2014 for for this source, and no one ever published it because it was just put away as like a weird AGN. And it's like, okay, we'll deal with this later. But now that we have this amazing like spectrum for it, all of a sudden we have this puzzle in front of us, right? In terms of number densities, the number density peaks at redshift sort of 5 to 6, and then it drops pretty steeply at redshifts below 3, I would say. There are a few sources below that for sure, but the number density overall drops pretty dramatically. So it's clearly early universe phenomenon more generally. Yeah.
All right, let's thank Anna again. And she's in B221. Please come and welcome her. As I noted, today's her second day, so she'll have a chance to meet all of you hopefully very soon. Thanks for coming.